Okay, let's start again. Let's not start late. So let me introduce the next presentation on the impact of modern architecture on sleep and wake-up mechanisms. So that presenters are Vladislav Vostrykh from Technical Engineering, who has more than 20 years experience in network technologies and software development. Great experience in the automotive sector, specializing in gateway development, validation, and e-architectures. And since 2014, he's led projects involving Ethernet power cycle validation, time synchronization, including safety time sync solutions. And he developed as well hardware-in-the-loop strategies and validated complex ECUs. And with Vladislav, Thomas Konigseder, I hope I told it correctly. Do I need to introduce Thomas, who is CTO at Technical Engineering? He holds special interest in software-defined vehicles, and at BMW initiated the creation of 10-base T1 and was involved in a multiple of activities leading to today's automotive Ethernet ecosystem. He also led the largest known automotive Ethernet architecture at that time, including multiple ECUs and Ethernet cameras. And since 2017, he supports OEM worldwide in e-architecture design, testing, and validation. So let's start. Let's come on stage.
Thank you, Fabrice. So, welcome. So I'm feeling like a Madonna, you see the microphone here. So I'm very happy to be here. So Vlad and me will show you some part about the things that are changing in the architecture, because not only Ethernet is evolving, e-architecture is evolving, and we will give you some background information. So Vlad, maybe you want to add some words on it? Let's start. So start is a good starting point. If you look to the pictures, you see a knob there, on-off. On-off is simple, but on-off sometimes isn't. So I would like to start the journey a little bit. Where do we come from? When we say we, I mean our automotive industry. So I called them the good old times. So it was a good time where you have a key in your car, you switch the car on, you switch the car off. The only exception you maybe have is that you have a position where you can listen to radio. This was the old times. The old times was the times where if the car was not starting, the primary root cause analysis was a little bit simple. So whether the starter was damaged at the machine, but any other battery failure, like the battery is discharged, damaged, so the battery itself cannot provide sufficient power. The electrical harness defects, there were a lot of problems on shortcuts and broken wires, but everything more or less under control, or some water ingress. So I call them still the good old times. Why? Because now we're talking about the Valley of Tears. And the Valley of Tears is not a joke. Sometimes something went out of control. So, as we all know, the more software functions are coming in the vehicle, it is absolutely clear that you cannot just have a key where you turn off and on the car, so components has to work even if the customer is not in the car. So, as a result, we try to wake up the cars via networks. We wake it up, everything fine so far. Sometimes it was a little bit too slow on the startup. But in the end, there's a lot of protocols going on. A lot of people were focused on only one scenario, and that's about waking up the network via the network. Open lines, TC10, can wake up mechanisms, or some traditional wake up lines. When you listen to this presentation, you will think, where is Ethernet? In their presentation, you will see Ethernet is not the main driver behind. Because I think it's important that you know your friend or your enemy if you want to win a war. So that means when we talk about Ethernet and how we use the Ethernet as an ecosystem, it's really important to understand the full context. But please do not forget, robust startup and shutdown of a vehicle in many operating states, and the transition is one of the most challenging tasks in the automotive field. So the challenge still remains because each ECU today has to control the shutdown on itself. So I call this the software off scenario. So that means this picture on the slide shows the ECU that is constantly power supplied via fuse, and the shutdown or the startup is decided by the ECU itself. So now you can imagine, by whatever having 100 ECUs on a car and having maybe even a FOTA, software update process, it could be the case that the one or the other ECU isn't like to shut down. So the shutdown sequence is triggered, but in any case, the problem occurs and the ECU doesn't fall to sleep. So the thing is, you will have a battery drain system, you will have a lot of problems to stabilize the full car. If you sell whatever, 1 million cars a year, you can imagine if you have a tiny problem, it's a big problem at the customer side. A lot of the things are software problems, extremely complex, and that's why some OEMs, and I did it on myself some couple of years ago when I worked for an OEM, we were introducing some special power modules that allow to switch off bad devices where we already know that it could be case that this device is not always falling down to sleep perfectly. The good news is now I'm talking about the light at the end of the tunnel. So what is the light at the end of the tunnel? It's a new introduction of the EE architecture. It's the eFuse solution or eFuse systems, where in the end there's a semiconductor used instead of the classic melt fuses. So in this fuses, switching off the current in case of any high current scenarios that is not okay. Instead of melting, it's switching off electronically. So the key advantage, and this picture is from Onsemi, it's not from us, it's just to show you it's not a local idea, it's a already known system all over the globe. The key advantages of such systems, you can have a fast and a precise protection. They are intelligent, they are resettable in case of a thing failing. In the past, if the fuse was melted, you have to repair it, and it was very difficult to access it. And it supports a lot of new features of modern vehicle architectures that will come later in case. So in the end, you can see this is a fuse that can be controlled and can be used as a switch as well, not only as a fuse. So this switch could be, or the switches, because every device more or less has then one switch on front, can be controlled by a centralized vehicle management system. So the question is, when you look to such eFuses, you have to know that they're more expensive than melt fuses. So the question is, why are they such a big trend? And there are main 3 points where makes eFuses as a must. And the 3 points are the following one. One thing is that the power supply in the past was a robust monster. Lead acid starting batteries, very heavy. But instead of this, we have much, much more complex batteries that has to have the required protection against the overload as well. If you don't protect these devices from overload, on an active management, you will have a global shutdown. Yeah? So on the other side, there is a lot of safety coming up. So that means you have to find a solution when, for example, it comes to electric steering. How do you take care that the electric steering is the last thing that is switched off of the car, not the first thing? So that means you have to switch off some non-safety components to use the minimum available battery for the important things as well. So active help for the so-called safe power supply systems. And there's a third part. The third part is the zonalization, saving a lot of costs in the harnesses and having local domains, local zones, where you will see the impact of this eFuses as well. So this concept is really now paving the way of the future for the next generation of vehicle power management systems. And now I'm coming to the point why this comes together with architecture and even together with the Ethernet system. I will show you a reference architecture. This is just an example. Of course, each zonal architecture looks a little bit different, but this is the example for it. And I'm very proud that there is an Ethernet backbone as a backbone, because this was my plan when I started with the Ethernet idea in the early beginning. But what you see in this picture is essential. You don't only see the communication, because in this group we talk about communication technologies. But e-architecture is more than only communication technologies. A lot of things has to be done with power supply, and power supply has been needed. So what you see in the picture is on the ground, you have the battery as the source of power. And then in the end, you have a very complex, in today's new systems, much more complex power distribution system that is distributing the central power to the zones. And out of the zone, inside the zones, the distribution is going on. So it's a local zone of power, local zone of power supply. And this is the main thing, not the communication network at all. This is the main thing, sells a lot of harness and a lot of cables. If you look to the red thin lines, and now think the red thin lines has to go full over the car to one power distributor, you can understand where the harness, the weight, and the costs are coming from. It's not only the communication system. It's a lot of things has to do with the power supply. So now when you see this setup here, you see that there will be active management systems, the so-called eFuses, normally integrated in some zonal controllers. These zonal controllers in this example are connected via Ethernet, but some of the power distributors can be connected to any other bus system as it can, or 10 megabit Ethernet, whatever you like. And this is, let's say, the core elements of such a system. So what you see, the power and switching on and switching off the power is part of the ecosystem. It's an active system. It's not a passive system as in the past. It is not a fuse that is switched off in case of error. It's a control switch that can be controlled on any life cycle, on, off. And that's why we have now different modes. And of course, a lot of other chances to wake up and to bring system to sleep. This is not just a simple start up and shutdown of a fuse, switch on, switch off, whenever you like it. It's very essential that it is controlled by a centralized system, because the complexity is extremely high. And Vlad will now show you a scenario as an example how such a startup and how such a shutdown could look like.
Thank you. So, and this is a scenario what we prepared for zonal architecture, but you can use it for domain architecture, you can use it for centralized architecture, you can use it for your smart home projects, do it yourself, because principles are the same. So, startup, we have only two things powered on. So eFuse, which is controlling our so-called vehicle state manager. All other issues are off. There are no sporadic startups, wake-ups, and so on, because without power, it will be complicated. And VSM in this case is also make controlling and observe some hardware IOs, I don't know, key, for example, door contacts, and then the standard wake-up stuff. And when it detects, so the startup process starts. First, we want to wake up the main power distributor. It can be several power distributors, but at some point you need this main power distributor to provide the big, thick lines to the zonals or your domains. You can use standard mechanism like CAN or wake-up line, must be fast. Then, yeah, probably you want to start the zonal, so you just power them on. You set vehicle state manager controls the power distributor. It sends commands, please turn these eFuses on. And the goal for power distributor is quite simple and can be done in safety, in fuzzy, functional safety conform way. You probably want also to wake up your Ethernet backbone, because it needs some time to wake up and you need it for your communication. And you can start the devices that you need. So what is important here is the startup sequence is actually completely under your control. So you can avoid these in-rush scenarios, the overload of the battery, what Thomas was saying, and intent. Another interesting use case is that auto, for example. Yeah? Can you flash 100 devices at the same time? Probably not. Do you want to keep 100 devices on during flash process of 5? Probably also not. Here you can control it easily. So important thing here is simplify complexity. The VSM itself can be really a monster because you need a lot of states in your car. You have different variants of car, and it will be really parameterized program. But you centralize complexity, and it's not democracy. So you really control everything. Yeah? This is the advantage here. And for the shutdown, so when everything is on, yeah, typical situation, but then for some reasons we start in the shutdown process, so it can be this something similar to network management, timeout, or it can be direct control channel from VSM to ECUs, so it can say, please go off, I don't need you, others, we are stopped, so please switch off. And in the good case, ECU reports, okay, I prepared to shut down, I saved all my data, so I don't care if you turn me off. And if you got the signal, then the only thing you need to do again to switch corresponding eFuse off. And even in bad case, when we have a bug and ECU is not going to sleep, you still have control. So instead of situation with battery drain when a vehicle cannot even start or open the door, you still have possibility to drive to a repair shop, for example. And in this case, after some time, you just switch off everybody who should not work. Also, you can implement here, integrate and implement battery monitoring tool. So for some long periods of time, you can really think to deactivate almost everything. For auto can be also important really to check that how much ECUs you can activate and deactivate. And so in here, the development circle is actually closed and we are back to hardware.
So thank you, Vlad, for the example. So of course, this was just a very simple example where we say some of the components are switched on, some of the components are switched off. Of course, we know that there will be components who has to be always be powered on. A telematic control unit has to be always powered on. That's not a problem. But even the telematic control unit will be always powered on such a system, and it can be switched off if there is any detection of any error, of any problem. And please do not forget, when a component is always on power on, everybody from the semiconductor business knows it, it's the runtime of the system that stays on. So that means even it's a cost down of the component itself. But so coming back, so the storyline is we don't have a key anymore, but a software component in the car have hundreds of keys now, switching the system on off. So the control is back. That does not mean it's simple, and we have to be very careful. So coming back to the conclusion, the physical key is not longer required. We can design a dedicated software component to control all the subsystems. And the introduction of active eFuses has a fundamental change of the vehicle power management. The question is now, why this had such an impact on Ethernet and the standardization? I think the colleagues from Thomas said it, we have to be a little careful in standardization. Sometimes we invest ourselves, we are thinking in our own process, we do not look outside the area, and we often do not understand what kind of other options do we have. So a wake-up via bus is not so important anymore as it was in the past, because there will be some components who need to be initially woken up, but as long as they are woken up, I can control the full power supply with a mass of eFuses. So switch on and switch off a component is the new way to control an on-off system. It's not the must to say everything is power supplied, and we have to make it available for wake-up via bus. We all know wake-up via bus looks nice, but we even know it costs a lot of money, it adds a lot of complexity, and it can create a lot of mistakes. So control is smarter, faster, and more flexible than ever if we set up the right concept. If you're interested in some right concept, again, this was just an example. You're always welcome to our company to see what we did. I'm already implementing a reference architecture, and our booth you can have some information as well about the configuration. So thank you very much for your attention, and ready for questions. Thank you.
Thank you, Vladislav. Thank you, Thomas. Any question? Okay.
Thank you very much. Very interesting topic. I have a question. So it means that even this eFuse system will have a global control of the completely system, Wakeup, shutdown.
Mm-hmm.
So you cover all use cases.
Yeah. So the important thing is that when we look to shutdown management, and now I'm working for a lot of OEMs, and often they're coming to our office and say we have a big shutdown problem. I'm looking to this shutdown problem and I see it's a kind of democratic shutdown mechanism with network management. It's not the problem of network management, it's how you do it. And the idea is to have a centralized software component in the car who knows every state, the state of power supply, the state of communication, the state of the car itself. And this is the master. And then the master can make a decision to make a shutdown or a needed startup. The good thing is, if you have a problem, you have only one component you have to fix, and then you can correct it. If not, you have a big distributed thing, and that's very difficult to control.
Okay, thank you. We long queue, so I give a priority for the next.
Yeah.
Hey, Thomas, thanks so much. You know, I totally agree with the centralized approach. We've been discussing this, I don't know for how long. So my question would be, we still need some sort of communication to the devices in order to prepare them to shut down,
Yes.
Stuff like that. Maybe even have a failure case where they shut down themselves.
Yes.
What does that mean for the communication we use? Do we stick with the network management, the automotive network management? Do we move over to that we actually use service discovery as a power control now, what we on purpose did not do in the past? Do we use the OEM channels that some of the new FIs supply? Where do we go with the communication on this?
So I can give you a very clear answer on it. You have to stay on a low-level communication level, so not about service, anything else. Go into a very simple communication method that it's the same on CAN, that's the same on Ethernet. So the messages, we go to a kind of low-level control communication. So because it's important that you control the stack on the lowest end from the startup up to the shutdown, so that there is no huge overhead of any service discovery in this concept. That allows a very important thing, because there's a lot of challenges in such a system. I didn't tell you every truth, okay? So the startup sequence is extremely essential, because you have to start up such a system, and when you have an active communication system that is needed to start up the power supply, you cannot start with an AutoSAR component as it is today, because you will need some 100 milliseconds. You have to optimize the startup, and by controlling the full system, the idea is that you have I call it always low-level message, NM style, as we did, Max, in the past, but use it in a global way. And then we have additional communication between the device itself and the master component on the other side, that they can exchange some, let's say, additional information, ready to sleep, not ready to sleep, whatever's happening.
Thanks.
And probably one more point here. So we need to modify software. We need something like run levels, what is not existing in AutoSAR. So there is a lot of work actually here. It's simple to present, but not so easy to implement.
Okay. One comment, first of all, TC10 doesn't come for free in the FIs, so if we could get rid of it, it would be a huge simplification. Nevertheless, I didn't really get it. I mean, you have to run the same algorithm to decide which node is on and off, no matter if you're using an eFuse or TC10. The only difference is it's distributed. And so does that really pay everything for everything?
So I think the important thing is a switch on and a switch off a component by power. That's a big change. The other thing is, when you look to TC10, it's not just a matter of what the PHY is doing. You have to look to the full ecosystem. You have to look to the switches. You have to look to the chain. So if you look at such a distributed system, you see a monster of a distributed system. It's very complex. It's a monster when you talk about zonal architectures. And you have so many dependencies on the startup sequence. With the power supply system, you have a kind of parallel wake-up mechanism automatically. And this is a huge impact. And that's why I'm not agree to say TC10 doesn't create a lot of overhead in the network design. On the PHY, maybe, because it just looks some patterns and then you start up and shut down, but you have to have the transportation scheme available in all of the scenarios.
Hello again, thank you for the presentation. Actually, I'm wondering, did you really have a look to the weekly architecture? How many components do you have really you can cut the power completely down? Because of, I expect there are some input and outputs attached to this component which can cause a wake up and you need to maybe frequently monitor these inputs. This is the first one. And on the other hand, I think this approach can create another problem which you have an opportunity to cut the power to an entity, but then you should be sure that every time you are cutting the power at the correct time. And it's creating a next problem that you need to handle. Yeah? These are the 2 points in my mind. Yeah?
So the answer for the first question, where you said there will be some components always powered on, you're right. You're right. There will be 5 to maximum 10, that's it. The rest will not be always powered on, due to different reasons. So there will be always a kind of core system who will check the input, the door handles, all the stuff. There will be some dedicated components. There is a big list normally at the OEMs what are the wake-up reasons. And to optimize the power supply when the car is not there, in the end you have some core designs that are triggering the initial wake-up of the car. This is one thing. The other thing, when we talk about who is switched on and who is not switched on in these cases, there are some things, especially in the safety area, it's very essential that the central architecture is not, let's say, limited to safety rules, because then you have a lot of problem to change the core of the central architecture, because every time you have to make an additional safety validation that this is switched on when it should be switched on. For this reason, there will be a second line of defense, I would call it, where within the slave, so that means the devices who has to switch on the power, they are active communication systems as well, and have the car state as well. It's a kind of second line. If they see, okay, there is a real scenario where I need the fuse, and the central master on safety limits, okay, and the central master is not switching the system on, he will take care to switch on the fuse. This is a kind of overlay mechanism to stabilize the full thing. But the decision who may have to make a startup and shutdown today is done today decentralized. So now I ask you one question. You have an error, and the error is distributed. How you can control about distributed errors? It's a mass. It's a problem. So that's why it's easier to control it on one side instead of leaving it to a lot of components.
Yeah, I understand. In the past, it was a bit domain approach because of there was a central domain controller and it was monitoring basically the bus. But actually, the question in my mind right now is a challenge. For sure, you don't need to answer. With the zonal architecture, we are really decreasing the number of the ECUs, and I'm really thinking, okay, how many ECUs there are really in the architecture that I can or I need to cut the power in case of some specific vehicle states, yeah?
A lot of, more than ever.
Okay, then because of maybe the hybrid architecture then?
Not only the hybrid, but if a zonal architecture doesn't mean you need less components. You have a lot of components down the zone, and this control has to be controlled.
Okay, thank you. Then I can give you.
Yeah, last question maybe.
Albrecht Schwarz from ETAS. It's more an architectural comment than a question. So the electrical energy management of a distributed system done via a management plane no surprise for me that there is a centralized approach followed here. My comment is rather power management should not be done in isolation of the other management categories inside a vehicle, because this is linked to the management of the on-vehicle communication system or application system.
Absolutely.
So we have different state models. We have here the power-saving state models, but also we have operational state models. So that manager should be part of an overall manager inside a vehicle. Yeah?
That's it.
That's it. So I'm happy to see that your company is following a centralized in-vehicle management approach, and this is relevant for TC19 in open lines.
Yeah, that's why we call it vehicle state manager and not power state manager. You're totally right. Agree.
Okay, thank you. I think we have to switch to the next presentation, but I invite the speakers to stay aside from the scene. And let me